Welcome back. This topic of phase rule is probably the last topic related to chemical equilibria. In the previous lecture, we had derived some general expressions to establish the thermodynamic criteria for chemical equilibrium. So we considered a system, a controlled mass, say, a reacting system, chemically reacting system that's under constant temperature and pressure, and combine the first and second law and then obtain the general condition that Gibbs free energy of the system is less than or equal to zero. At equilibrium, it is zero. It's good for you to go through the logic, how we arrived at this result. Instead of just memorizing the result, the logic is so useful for you to assimilate. And then that helped us in determining what composition will be present at equilibrium. Supposing there is a chemically reacting system, it is not necessary that in all the reactants have to get converted to products. The composition that is present at equilibrium is the one that minimizes Gibbs free energy. Right? So, and we used Gibbs free energy because that is the relevant thermodynamic function when the system is under constant temperature and pressure. Usually this is the temperature and pressure of the ambient atmosphere. Starting with this relationship, we also derived the general criteria for chemical equilibrium. Okay, so here G, the small g, is the chemical potential or molar Gibbs free energy. So the common symbol that is utilized everywhere is mu, but this textbook uses this particular symbol. So this is the reaction coefficient. So this is the criterion for chemical equilibrium. And then to utilize this in principle, you should also know what is the general expression for chemical potential. So typically you derive such an expression for assuming that the system is an ideal gas. So in this case, we are looking at an ideal gas reaction, chemically reacting mixture. And then this is a general expression for chemical potential of an ideal gas. So this is the partial pressure of the component I. And all the reactants and products are at temperature T. Incorporating this chemical potential expression into this expression gives you the expression for equilibrium constant. It is a constant at a particular temperature. And this can be expressed in terms of the free energy changes involved in the reaction, okay, under some standard condition. So this, of course, changes with T, and this provides the basis for Lee-Chatelier principle that you've seen from high school. So we derived how Kp changes as a function of temperature, and we derived the Van 't Hoff equation. The way reaction equilibrium changes depends upon the delta H of the reaction, whether it's exothermic or endothermic. The system reaction constant will change in different ways. Expressing enthalpies using specific heat capacity at constant pressure, we were able to simplify the Van 't Hoff equation and then arrive at the so-called Kirchhoff's equation. So this expression, we got it from a very good textbook in chemical thermodynamics called Principles of Chemical Equilibrium by Kenneth Denbigh. So it's a slightly advanced textbook, but it's a very good textbook. So if you're interested in chemical thermodynamics, you can refer to that book. In addition to this, in the last lecture, we did two important things. Okay, so the last lecture gave us a closure on assembling all the relevant fundamental equations of thermodynamics. Just to reiterate, depending upon the way experiment is conducted. Okay, so these variables tells you how the experiments are conducted, which is kept a constant. For example, in this experiment, you are keeping temperature, pressure, and total number of molecules are constant. For such a boundary condition, for such an experiment, the natural thermodynamic potential is Gibbs free energy. That takes a extremum value, in this case, minimum value. Okay? So dG is expressed as an intensive variable, extensive variable, intensive variable, extensive variable, and this is the chemical potential of a component J. Okay, and this the D and J is a variation in chemical component J. So if the experiment is done in a different manner, for example, in this case of keeping temperature a constant, volume a constant, total number of molecules a constant, the relevant thermodynamic function is the Helmholtz free energy. Corresponding to that, there is a different fundamental equation. Okay, so this is a very important table. You should assimilate this. And we also summarized the rationale behind different thermodynamic functions. So you would see a zoo of thermodynamic functions. Not every thermodynamic relationship has an equal status. There are something that are fundamental and useful. So that is it tells you some functions which in a particular experimental condition takes an extremal value and gives you a criteria for equilibrium. These are these functions. Okay, these are these functions. Useful but not fundamental. Okay, so we also summarize that which thermodynamic functions are useful but not fundamental, that will help in assembling a fundamental equation. Complete but useful. Okay, we had talked some such functions, and incomplete. So incomplete is easy to identify when a pair of conjugate variables, P and V are conjugate variables, mu and N are conjugate variables. Okay, so these are not a unique way of specifying entropy, or this is not a unique way of specifying internal energy. Okay, so both these slides, the previous slide and this slide, are taken from this very good textbook, Molecular Driving Force by Kenneth Dell and Broomberg. So, so both these slides are very important and brings in a closure to this topic. So you should assimilate and make sure you understand this well. And if there are questions, we can take it up in the discussion. Moving on, we will relook at Gibbs Phase Rule. We have utilized the Gibbs Phase Rule in the first part of this course, but we're just taking a relook at this because we have introduced this concept of chemical potential. So what does Gibbs Phase Rule tell you? It gives you a simple relationship between degrees of freedom, number of components, and number of phases. So what is degrees of freedom? These are thermodynamic variables that you can change without changing the phase of a system. You are not creating a new phase or destroying a new phase. How many such thermodynamic variables are present in the system is a measure of degrees of freedom. Number of components and phases are rather easily defined. So the next few slides I've taken it from this very good online material prepared by Professor Anand Subramaniam in Material Science Engineering in IIT Kanpur. He has a whole lot of slides on various topics in material science and engineering. So you can take, and it's freely available. So you should make use of that in case you're interested in material science and engineering or many topics relevant to material science. All right. So what is the Gibbs Phase Rule? We are stated this without deriving it in the earlier part of the class. So this is the number of degrees of freedom available in the system. This is the number of components, number of phases present, and 2. We'll see why we get 2. This 2 is because of pressure and T are the thermodynamic variable of relevance. Okay, first we will list out the variables present in the system. Okay, so all these things are more easily addressed in the context of certain phase diagrams. We'll see, we'll address this towards the end of this lecture. So variables present in the system are composition variables, okay, plus the thermodynamic variable. How many composition variables are available to you? In each phase, there are C-1 composition variables. For example, if you take mole fraction, if there are n components, x1 is the mole fraction of component 1, x1 plus x2 plus x3 plus xn should add up to 1, right? So you need not have C composition variable, just C-1 composition variables are enough to specify the composition of a particular phase, and you have P such phases, let's say. So P times C-1 is the total number of compositional variables available to you. And then typically the most common thermodynamic variables you are trying to control or trying to change are pressure and temperature. In most of material science, we address solid phase behavior, alloy phase diagrams, and so on. So it is easy to do these experiments at constant pressure and temperature. For example, if you have gases, probably you do it at constant volume and so on. Okay, so these can be taken into account. So total number of variables available in the system that can potentially be varied are P times C-1 plus 2. The degrees of freedom can at most be equal to this much, but usually it will be less than this number. Okay, we'll see why it is less than this number. We are going to utilize one more constraint on the system, because each phase, there are many phases present and there are many components present in each phase. So each phase has many components. When such is the scenario, if you take a component A and this component can readily exchange between phase A, phase B, phase gamma, phase alpha, phase beta, phase gamma. This is the way typically phases are specified in material science and engineering. So if A is in equilibrium, what does that mean? Then that means that the chemical potential of component A in alpha phase is the same as chemical potential of component A in beta phase, chemical potential of component A in gamma phase. If this were not so, A will readjust itself to lower the overall free energy. Okay? So at chemical equilibrium of component A, this constraint is maintained. So such a constraint on chemical potentials can be written for all the components present in the system. All right. So what is the degree of freedom available to you? So that depends upon the constraints you have. So with this constraint, for a particular component, you can write P-1 constraints, right? So I take a component 1, I can take alpha in equilibrium with beta, alpha in equilibrium with gamma, and so on. So for one component, have P-1 constraint. For C components, I have C times P-1 constraints. So the total number of degrees of freedom for this system is the total number of variables available in the system that we had documented in the earlier slide as P times C-1 plus 2 minus the number of constraints or number of constraining relationship between the variables, that is C times P-1. So simple algebra will tell you this is the equation for the Gibbs phase rule. F is equal to C minus P plus 2. How do you better understand Gibbs phase rule? This tells you how many variables that you can choose independently. You can vary them in such a manner no new phase is created or destroyed. Okay, so this is the number of components, number of things that you can control. Okay, you can control the compositions, what I'm adding into the system, right? Adding or removing into the system. And 2 comes because you're constraining, controlling pressure and temperature. And this is what the system controls. The number of phases present is automatically fixed not by you, but by the system itself. You can control this, you can vary this. Because of these 2, the system fixes this. So we will implement this in the next slide. For example, just putting this formula for different kinds of phase diagram. For example, if you have only one component, it's called unary phase diagram. If you have 2 components, called binary phase diagram. If you have 3 components, called ternary phase diagram, then quaternary phase diagram. In material science, this plays a very, very central role, and the nature of phase diagrams are complex than what you see in other branches of engineering. In chemical engineering, you typically see phase diagrams involving liquid that can also get complex. Azeotropic systems can get complex. In material science and engineering, you typically deal with solids, alloy phase diagrams. They can also get very, very complex. We're just implementing this rule, that is, this rule F is equal to C minus P plus 2. For example, if you take 2 components, the total number of variables, degrees of freedom, and so on, right? So why sometimes we say the degrees of freedom is C minus P plus 1 is you assume that you are doing the experiment at atmospheric pressure, and the only thing you are varying is the temperature. So sometimes the form of the Gibbs phase rule might be different. Instead of C minus P plus 2, you might see C minus P plus 1, because automatically it is assumed that pressure is center constant. All right. So if you have a 2-component system, let's say you're looking at a binary phase diagram. So if you have a single phase region, the degrees of freedom is 2. If you have, let's say, 3-phase coexistence, okay, 3 phases are in equilibrium with each other, then implementing the formula, you would see that the degrees of freedom is 0. That means you really do not have a choice on any free variable. Okay, so, and then if you want the system to have 4 phases, that's not possible, because the degrees of freedom will turn out to be negative. At most, the degrees of freedom can be 0. That means for a particular system, there's one point, okay, wherein all the 3 phases are in equilibrium with each other for a 2-component system, right? So we will clarify this further in the context of a particular phase diagram in the next slide. For example, if you have a 3-component system, you may have even 4 phases in equilibrium with each other, because degrees of freedom can be 0 for a 3-component ternary mixture with 4 phases in equilibrium with each other. Okay, so all right. So let us take a phase diagram that you see in, I think this is for iron. It's a unary phase diagram. Unary phase diagram. It has only 1-component system, so C equal to 1. If you notice, the pressures which you observe is really large. Okay, so if you want to look at phase diagram for alloys, okay, the temperatures range and the pressure range is much more than what you see for gases and liquids. All right. So if you are having C equal to 1, in this case, P is equal to 1. So the degree of freedom is, degrees of freedom is 2, okay, just by implementing C minus P plus 2. That means what? I can vary the temperature and pressure independently, and I don't see any appearance or destruction of phase. Okay, I can still be in this domain of single phase region. I can vary, let's say, temperature independently, keeping pressure a constant, or keeping temperature a constant, I can vary the pressure independently. So that is possible in this single phase region, in this single phase region, okay, and all single phase regions. Let us move on. Let us look at a two-phase coexistence region. So in this region, the liquid phase is in coexistence with a particular solid phase. So C remains 1. Phase, number of phases is 2. So C minus 2, P plus 2 happens to be 1. That means I can vary only one thing independently. I cannot vary two things independently. Okay, so so here I could vary two things independently, but here I can vary only one thing independently. So that is, if I, let's say, vary the temperature, the pressure is automatically fixed. Okay, so if I want to stay in the two-phase coexistence region, if I choose a temperature, I cannot vary pressure independently. Okay, so pressure is automatically fixed. Here, I could, for a particular temperature, I can have a series of pressure, or a particular pressure, I can have a series of temperature. Okay, and still remain in this region. But here, once I choose a particular temperature, let's say here, independently, I don't have a freedom on the pressure. Corresponding to this particular point, okay, it's corresponding to this particular temperature, pressure is automatically fixed. Okay, so that is true for any two-phase coexistence region. This is a two-phase coexistence line. This is a two-phase coexistence line, and this is a two-phase coexistence line. Let us go to a region where three components are present. So that is this region and in this region. In fact, this is not a region, this is actually a point. Okay, why so? If I have component to be 1, phase to be 0, but just by implementing Gibbs phase rule, C minus P plus 2, I have the degree of freedom to be 0. Once I fix these three phases to be in equilibrium, for this particular system, let's say I really don't have any choice. Okay, so if I want the equilibrium of these three phases, the system decides when that is possible. You really do not have a choice. So instead of coexistence line, I have a point, coexistence point. I have a coexistence region in a single phase region. I have a coexistence line if in a two-phase region. I have a coexistence point if I have three phases in equilibrium. So I can have three phases in equilibrium here, three different phases in equilibrium at this point. All right. So this is for a unary phase diagram. So for a unary phase diagram, at most, if I look at, okay, so at most I can have three phases in equilibrium. Okay. All right. That's what is the implication. So I chose phase diagram. Again, it's a very important phase diagram because iron has determined the iron-carbon diagram, for example, or the properties of iron has had a great effect in the way civilization has developed. Okay, so you should be aware of different kinds of phase diagram. For water, if water is the phase diagram that is most important, probably the phase diagram involving iron closely follows in importance. All right, so let me stop here. So we have completed this entire topic of chemical phase equilibria, and we will switch gears and move on to a topic that is important, of great importance, in especially in mechanical engineering. We'll start with gas power cycle. Thank you.